Hey, what's up, everyone? So since I'm not on campus today, but I just wanted to help you guys, I thought I'd go over one more exam, and so we're gonna make use of this Facebook Live thing, so everyone can kind of watch and ask questions as I'm going. So this is the day before your test. It's Thursday. Your test is on the 22nd tomorrow, and it's usually at 7, I believe. Y'all probably know better than I do about that, what time it is, but I'm pretty sure it's 7. So this is the point where you should kind of have gone through most of the exams, right? And I purposely didn't send you guys the 2016 one yet because I wanted y'all to, be able to kind of use that as your last main source of material to kind of compare as to how you would do on the actual exam, which is tomorrow. So it's always good to have like a fresh exam that you haven't like touched yet to kind of just test yourself in terms of how good you are with everything. So today we're gonna do the 2012 exam. Okay, and the first question on the 2012 exam, y'all should have this one, by the way. I shared it with everyone that's in this chat. So let's start off with the first question. Also, if anybody has questions, please just type it in, and I'm pretty sure I'll be able to see it. And I'll just slow down and go from there. Alright, so we have this structure. This is the first question on the nomenclature for this test. So we're pretty much going to have to see in which... Let me get another color pen, 1 second. Okay, so we have to just kind of get good with how to start numbering these. So there's 3 things that you need to know. You want the longest chain, right? You need the longest chain. And at the same time, while making that long chain, you also want to start that counting of the chain so you have the lowest number for the substituent possible. And the third thing is to try to have the most amount of subs possible. Right? Okay. So, keeping that in mind, a good thing with nomenclature is to just see where it would be incorrect to start numbering from, right? So, if you were to start... Actually, I drew... 1 second. There we go. Okay. So, a good thing to do is just to see which way you don't want to number the groups by. So, just so we can have an idea, hold on 1 second, I think I'm looking on the wrong test. No, never mind, we're good. Okay, so, yeah, let's start with figuring out where the wrong side would be. So if we were to start from here, we'd have 1, 2, 3, 4, 5, 6, 7, 8, right? And that would give us subs on 2, 5, and 6. So that's one way, right? If we were to do it from this way, we'd have 1, so I'm going to write 2, 5, and 6. So that was the first way. And then this way we have 1, 2, 3, 4, 5, 6, 7, 8. And we have subs on 3, 4, and 7. And if we were to go this way, we just get a shorter chain compared to 8, right? 1, 2, 3, 4, 5, 6, 7. The only other way that I didn't do is this way. 1, 2, 3, 4, 5, 6, 7, 8. This way we get subs on 2, 3, and 7. So we know this is not it because it's like that with 3 first. And then 2 and 3 is smaller than 2 and 5, so that's how we know that this is the correct way to go. Now, the best thing to do is to write what the parent is for this, so that's going to be 8 carbons long, so the parent is going to be octane. And under here we can just start writing the substituents we have. So on 2 we have methyl, right there, and on 3 we have methyl again, and on 4 we have this gigantic substituent. So let's write 4 here and let's go to it. Okay, so on 4 we have this substituent which has a substituent on it as well. So what you want to do is, once you figure out that this whole thing's a substituent and it's not part of the parent, you want to number the longest way you can in one continuous fashion. So this is the first one, second, and third. It doesn't matter which way I went because they're the same amount of carbons, right? I could have done 1, 2, 3, and it would have been the same identical substituent on the other side. So that's not a problem, okay? So what we do need to do now is we see that on that fourth number for the substituent, on that first carbon which starts the substituent, we have to see what kind of a group is coming off of it. And as you can see, this whole group is a CH2, CH3. So what you want to do is put parentheses here and then note where on the 4 is that substituent, and we know it's on 1. And then that group CH2, CH3 is ethyl. And then we write the main substituent that substituent's on, which is this. It's a 3-carbon chain, and since it's a substituent, you have to also end that in YL just like this. Okay, so we have one more substituent left. It's on 7, and that's also going to be a methyl. So this is a good way to do it, just to make like a little list like this and then write the parent on top, so you can kind of know what the final answer should look like. So to finish this off, we again go with alphabetical to know which part goes first. This starts with M, E, M, and M. So 3 of them are the same, but E comes before M in the alphabet, so we know this gigantic group is going to go first. So the final answer is going to be 4, 1, ethyl, propyl, and we have 3 groups with methyls on them. So that's going to tell you have to first put the numbers in order like this, and then write trimethyl octane. Okay? So your final answer is 4, 1, ethyl, propyl, 2, 3, 7, trimethyl octane. That's the first one. Okay? Next. Okay, so let's do this. Okay, so the first thing to do with any nomenclature question is we have to see what the parent is of the actual figure that they get, she gives you, right? So we know, as we've learned in all the sessions we've gone through as a class together, is that this chair diagram, this is called a cyclohexane chair conformation, okay? And pretty much what this is the same thing as a 6-membered ring. It's just showed in a different orientation. So we know that this parent is going to be cyclohexane, okay? So again, we can make our little list. We'll come back and figure out what the numbers are later for these two substituents here. But let's figure out what these substituents first are. If you refer to the email that I sent to everyone, it has a good like breakdown of bullet pointed notes, and on the last page of that email I have a good cheat sheet that has all of the substituents listed out, what their names are and what they look like. And if you memorize that, you should know what this group is just by looking at it. It has the forked end, and we've learned that this group is called isopropyl. It's called propyl because there's 3 carbons here. There's 1, 2, 3, and then iso because it's isolated into a fork. Alright? The next group is, when you look at it, you're going to kind of maybe be confused in terms of how this looks like. But again, the best thing to do is to convert it into line angle. So I'm going to draw this little squiggly line just to show where that bond is coming off, okay? So this line that I just drew corresponds to this line that's right here, okay? So we have a CH2. There's the CH2 right there. And then off of that CH2 we have a carbon that has 2 CH2 CH3 groups coming off of it. And the CH2 CH3 group is referred to as an ethyl, and there's 2 of them because there's this subscript of 2. Right? So we have that first one, and we have that second one. And this H over here is understood to be on this carbon. I'm not going to draw it because it's kind of like intuitive just to know that there's a hydrogen coming off there, so it's good practice to just kind of understand where the hydrogens are without drawing them now that you're about to get through this first test. Alright, so as you can see, this looks to be similar to this question in terms of a substituent being on another substituent. So that's what we're going to find out, what the name and numbering for this one's going to be. Okay? So we have this first carbon, second, and then off of this second one we can go either way again because they're both identical going from either direction, right? So I'll go this way, 3, 4. So the number that this one will be on is did I actually draw this right? Let me double check. Yes, I did. Okay, good. So we have this group with 4 on it, meaning that the end of this substituent should end like this with butyl, right? The only thing we need to know is the number that it's coming off of, which is going to be 2, because off of this second one is this other substituent, and that substituent that's coming off of it is an ethyl. So we have 2-ethyl butyl. Okay. Now that we have the substituents written out like this, we can now determine what the numbering is going to be for these. So again, for the numbering, we're going to look at alphabetical, I versus E, right? So E comes before I in the alphabet, so we know that this group is going to go first. So knowing that this big group is going to go first, we can label a 1 on the group. And now the question is, which way do we go around to number the rest of this chair? And as you can see, they're both placed in the opposite directions. And no matter which way you actually go, it's going to give you the same number on this substituent. So if you go 2, 3, 4, 5, 6, or you can even go 1, 2, 3, 4 again. So it doesn't really matter. The point is that the numbers would be the same. So we know that this one is going to be on the 4th spot. So there is one more. Actually, let's write down what we have so far. So we have that 1, 2-ethyl butyl, And then that other one is on 4, and that was an isopropyl. And the parent, running out of room here, right, cyclohexane. Okay? So we're missing one more very important thing, which is always crucial with chaired conformations, is we have to look at what the orientation of this entire structure is according to the substituents, right? So as you can see, this group over here is pointing up, and this group over here is pointing down. So if they're both pointing in opposite directions, up or down, we know it's going to be trans, right? So the final answer for this one is going to be trans 1, 2-ethylbutyl, 4-isopropyl cyclohexane. Okay? So that was that one. Next. Okay. So this is all number 1. This is like part B or part C. So I'm going to stick to that. Okay, so this is 1C for the next question. So this is actually a really, really good question right here, because this is the first example that y'all are probably seeing if you didn't do this exam yet, where you have 2 closed rings. So you might think that these would be the substituents, but that's not the case, and we'll see why in just a second. So again, we know that we want the longest chain, and we want the lowest number for the substituents possible. In doing that, we also want the most amount of those substituents possible. When I say number, I mean like what we did over here with the 2, 5, 6, 3, 4, 7, 2, 3, 7. Like we compared the numbers for where they would be if we counted from different spots. And this just means like you want a lot of them as possible, right? Okay. So here's the question. And yeah, so let's go forward with that. We know that this over here is a 6-membered ring, right? And then this over here is a 4-membered ring. But if you look, if you count from here, it's 1, 2, 3, 4, 5, 6, 7. So 7 would give you the longest chain. But now the question is, which side do we start from? If you do it from here, 1, 2, 3, 4, you have a substituent on 4 on your first spot. But if you do it from here, you have it on 3. So we want that lowest number, right? So that's how we know that we need to number from this side over here. 4, 5, 6, and 7. Hold on, give me 1 second. Okay, sorry about that. Back to the question again. So we know that we have to do it from here because of that difference in the low number of the substituents. So now what we need to do is just write out what the parent is again. The parent is a 7-carbon structure. 7 is heptane. And our first substituent is going to be on 3. So we write 3, and from there we write cyclohex. But this is very important. We know that this substituent is coming off the 3rd carbon, right? And that this is a this is a substituent. We're not going to end it at A and E. If it's A and E, then it has to be the parent, like this is, right? So what we're going to do, this is super important. A lot of people might not understand this or remember this, but it's supposed to end in YL, 3-cyclohexyl, okay? So 4 is pretty much very similar to that one, but this is what's this going to be? So this is a 4-membered ring. We know it's butyl, so cyclobute, not tane, not A and E. Don't be confused because it's a closed ring that it's going to end in A and E. This is a substituent, so it's going to end in YL, just like all of these did, right? Okay, so that is it for that one. Now what we need to do is figure out which one goes first in terms of the priority, right? So cyclo, these are all the same, but first point of difference is right here with H and B. So So the one that starts with B is going to go first. So the final answer for this one is going to be 4-cyclobutyl, 3-cyclohexylheptane, right? There we go. That's that one. Okay. And we have one more left for the nomenclature before we go to facts. So let's do that one. So in this question, she gave you the actual name, right? And she's asking you to draw this one. And usually if she has this on the exam, it's usually always the last one. I don't know why, but she does that. Alright, I want to make sure I wrote it right. 5-sec-butyl, 4-ethyl, 6-neopentaldecane. Okay, so the first thing you want to do always for this this type of a nomenclature question is to always know what your parent is. And that's the first thing you want to do. So the parent we know is decane. So what we're going to do is just make that 10 carbon parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have our substituents numbered out, so we can just start from the first one, right? It's saying it's on 5, so 1, 2, 3, 4, 5. I'm going to make a line coming down for that substituent, and it says that it's sec-butyl, so it's that special form of the four-numbered substituent. So it's going to look like this, and you can remember sec-butyl because sec stands for secondary, and if you look off that substituent bond, there's 2 carbons directly coming after it. Like from this carbon, there's 2 coming off, and this carbon is considered a secondary carbon, so you can kind of refer to that as sec-butyl, so you can kind of remember that. So that's on the 5th one, 1, 2, 3, 4, 5. The next substituent says 4-ethyl, so 1, 2, 3, 4. Go to 4 and write down what it's going to look like. And then next one is 6-neopentyl. Again, so let's do it first. 1, 2, 3, 4, 5, 6. And neopentyl is a different form of a 5-membered ring. I mean, not a ring, a 5-membered carbon structure. And if you refer to that cheat sheet I was just referring to earlier, when we started this test, the cheat sheet has this on there too, and I'm sure it's on your notes for class as well, and the notes from my sessions that we do every week. And neopentyl looks like that, okay? 1, 2, 3, 4, 5 carbons. So that's what your final answer for D is going to look like. Okay, so let's keep on going. Alright, so now we're on the facts question part of this test. Okay, so this question is asking you to draw a proper Lewis structure for the condensed formula below. And the condensed formula below that they have is this. Okay, so she gave you this, and it says to be sure to show lone pairs and formal charges, right? Okay, so let me open the periodic table. I can refer to that as I'm going. Put this on charge. Okay. So we have to make the Lewis structure and show lone pairs and show formal charges. So the way we determine out of these two which one is going to be in the middle is whichever one so So like you can kind of tell just by looking at it that the aluminum would be in the middle because there's 3 chlorines that it would surround. So we have that first part. Here's the chlorine on the aluminum. Here's the second one, and here's the third one. Okay, so this is all one structure, right? But so we have to continue it going on from this side. But before we do that, we have to see what aluminum's valence number is to know how many bonds it wants, right? And if you look on the periodic table, aluminum is on the 3rd column or the 3rd group. So we know that it's going to want 3 bonds, but this question is showing that it's supposed to be completely one structure, right? So we have to show that there's another bond coming off of it that's connecting with this O over here. And seeing that this is happening already, valence number for aluminum is 3, but this has 4 bonds, meaning it's overly satisfied. We know that we're going to have an anion over here. Okay, we'll double check with the formal charges in terms of what that number is, but we know it's going to be a minus charge because it's overly satisfied by 1 extra bond. Okay, so let's keep on going, and off of that oxygen we have a methyl group, and off of that oxygen we have another methyl group. So we have 2 methyl groups coming off of it just like this. And yeah, I think I'll just show the hydrogens as well coming off of that carbon so it can be a little more clear. Typically with Lewis diagrams you might want to draw them because everything's supposed to be shown kind of clearly. So next we see also that chlorine's valence number is 7, right? So we have 1 bond here, 2, 3, 4, 5, 6, 7 for that valence number, 1 bond there, 2, 3, 4, 5, 6, 7 for that one, and then same thing, 1, 2, 3, 4, 5, 6, 7. So we're done with the chlorines. We put the charge on the aluminum. Now what we have to do is see valence number for oxygen. Valence number for oxygen is 6. So we have 1, 2, 3. One, 2, 3, 4, 5, 6, 7, 8 to fill its octet. But we only have 3 bonds on this, right? So if we only have 3 bonds on it, it means that it's not it's not satisfied. It doesn't have enough because it doesn't. It would only satisfy the octet if those lone pairs were there. But since they're not, you have to make a cation, or not a cation. Cations for carbon. You have to put a positive charge because of the fact that you are lacking that extra bond or extra lone pair to satisfy the octet. So if we look back on this aluminum here, we know that its valence number was 3, right? Valence number for aluminum is 3. Formal charge calculation is valence number minus sticks and dots. The sticks around aluminum are 4. So the answer for that charge is -1. So that's why there's a negative there, right? And on the oxygen, we know that its charge, its valence number, so this is for aluminum. Valence number for oxygen is 6. And over here we have 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5. So the thing is like if you remember with the carbon double bonded with the oxygen, there's 1, 2, 3, 4, 5, 6, 7, 8. This is how it's supposed to look to satisfy its octet, right? The thing is this whole structure doesn't necessarily interact with this with 1 bond like this in the middle. There's like a the reason that these even attract to each other is because that this is positively charged and this is negatively charged. It's like when NaCl is in the environment, or when it's together, they separate, and then they come together to make it, because both of these opposites attract. So that's why I drew like a little squiggly in the middle to show that there's going to be some type of interaction between them, but they're not actually connected in your structure, right? So if they're not connected, then that will give you that one pair of lone pairs on that oxygen. So even though they do have that pair, right now it's still not an octet. 1, 2, 3, 4, 5, 6. So it needs 2 more, so it needs more, so that's why it's a plus. And you subtract it by 1, 2, 3, 4. So you get 2. So you know that it's going to be a plus, but in the actual question, it doesn't say to like calculate the formal charge. It wants to know what charge will actually be. So there you go. We know this is going to be positive, that's going to be negative. So your final answer is going to look like that. Okay. Next question. Okay, next question is saying to place the compounds in order of increasing melting point. So increasing melting point order. Okay, so let's draw the structures. So with melting point and boiling point, we learned that there's really one important thing that we need to look at with that, which is branching. Branching increases melting point, but branching decreases boiling point. But the thing is that branching doesn't always give you the correct answer. If you're looking at alkane structures with no atoms on it, meaning just like this with no oxygen, nitrogen, sulfur, or any type of atom besides a carbon, you can definitely always use branching. But the thing is if there's a structure that has atoms on it, branching won't always work for you. We'll go over an example at the end of this test so you can kind of understand what I'm talking about, but for now let's kind of finish with this test so we can get through this, but I'll definitely explain what I'm talking about in just a second, okay? So we know that we're doing this in order of increased melting point, so we're going to be focusing on this trend. We want a lot of branching for the high melting point, and if you look at the structure, the one that seems to have the highest branching is this one, because there's more substituents on this structure coming off than this one. Even though it's on the same carbons, this one has 2 coming off this one. So we know that this one's going to be the highest melting point. And then when we compare this, we see this one has 2 while this one has 1. So that's how we know that this one's going to be second in melting point and this one's going to be first. There you go. And again, if you don't want to think about too many things to memorize, but right now it's kind of basic, you can just learn it one way and then flip it if it asks it the opposite way, right? Like, so you can just answer in your mind with melting point and then just flip it if the question asks for boiling point. So that's just something you can maybe do if you think it's convenient for you. Okay, number 4 now. This one's saying to place the compounds in order of increasing solubility in water. Okay, and here are the structures. Okay, so what does solubility mean? Solubility means just you need to remember 3 words with this. Very simple. Y'all have learned this in Gen Chem. Like dissolves like. So pretty much we want the best situation for solubility to occur in water if the structure is most like water. And what do we know about water? There's a intermolecular force with water that is one of the highest in all of intermolecular forces, and that's hydrogen bonding. And hydrogen bonding is what we're going to be looking for in all of these structures. So if we look at the first one, we see that it has that OH group, right? Anything with NH, FH, OH are usually good indicators of hydrogen bonding present in the structure, right? So we have water, it has OH, and we have this O, this OH, and this NH. So if you look at it, it seems like this one's going to be the most soluble or dissolvable in water because it's the most similar to it. So since it's the most similar to it, it's going to be the increasing solubility component that'll go with water the best, right? The reason this one doesn't is because if you look at it, there's not a proton source directly on the oxygen. The H proton sources are directly on these carbons, so this is a deprotonated oxygen. This structure actually is called an ether. Okay, an ether is similar if you look at it to this, but you have to know that it's not protonated. There's no H plus here. Ethers are very, 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 you need to remember this, very insoluble in water or anything with hydrogen bonding. So that's super, super important. And if you compare the first one and the third one, you can see that this has NH. So that's a good indicator of hydrogen bonding. But the reason it's less than this is because this was OH, which is exactly what the question was asking with water having OH. So this is going to be the most soluble. This will be the next soluble one. And given what I just talked about with an ether, which is what this is, it would be last. Okay? So that's kind of what I was talking about with this question over here. Like, let's say you were given a structure like this versus this versus this. So like, let me just circle those. This, this, and this. Okay? And the question asked you to put these in order of the increasing boiling point. Okay? Even if this group had a substituent coming off this carbon in the middle, if this group over here had like 3 groups coming off of it, aka branching, if you didn't understand what I just said, you'd think that because this one has the most branching, you'd say this one has the highest boiling point. But in fact, hydrogen bonding is one of the highest intermolecular forces there are, and it would actually be this structure that has the highest boiling point because it's an actual alcohol, and alcohols are things with OH groups on them. So even though this one would have higher branching, this one would have the higher boiling point. So that's a good indicator of how branching doesn't necessarily always answer the question for boiling point and melting point. It always does if you have alkanes like this, but if you have atoms on the carbons like this, this would be the most high boiling point structure. And ethers would just be horrible. Like, you know, they would just they don't compare with anything that has hydrogen bonding because their solubility is a lot less compared to anything else, right, that we just talked about, because there's not a proton source on the oxygen. So out of these 3, this one would have the highest boiling point, even though this one has that more branching. So that's just something that you should definitely try to factor into your minds and memorize, you know what I'm saying? Okay, next, so keep on going. We're on the 5th question now. Okay, so this one is a resonance structure question. So resonance, and resonance is usually always the same. It just gives you a structure and says circle the major contributor. Right? Okay. So the structure she gave you in this question is a 5-membered ring with these groups and bond formations on them. Okay, so this is the structure that she gives you for the test, and yeah, so what we need to remember is that carbocations mean it doesn't have enough bonds. Slash domains, I guess you could say. And carb anions means it has too many bonds or domains. That's why, since it doesn't have enough, you move to the plus, and since this has too many, you move away from minus. So that's something you should definitely kind of already know, but if you don't, then it's a good thing to memorize right now. That way you'll never get any resonance questions wrong. So as you can see, we have 2 adjacent double bonds next to this carbocation. So we have the option of moving it from moving this bond over here or this bond over here. I'm going to go ahead and move this bond here first. And again, it's very important to note those double-sided arrows. If you do not show those double-sided arrows, she's not going to give you the points for that question. So this stays exactly where it was. We didn't touch it. We didn't touch this double bond either. And you can just put the same structures that were around it. So now, since we moved the double bond there, it's going to be here now. And now that we moved that double bond there, this bond over here, which was right there, is now unsatisfied. It has not enough bonds around it, so now the carbocation moved from there to here because this bond moved. Moving this up there now created a lack of bonding on this carbon right here, so that's why there's a carbocation. Next, we know that this nitrogen has no charge on it because it wasn't given to us with a charge on it. So I'm just gonna, this is a side note, don't write this on your test. Like if you were doing this question, don't write this as a part of your answer. This is just a side note, okay? I'm converting this down over here, okay? So here's my nitrogen. On that nitrogen are 2 methyl groups. And then on that nitrogen is this bond that's coming from the ring, right? So that's representative of that. I'm just going to write ring here. I'm not going to draw it, okay? On the nitrogen, we have no charge. So if we have no charge, that means that there's going to be lone pairs on this nitrogen. If we draw the lone pairs, we see that there's 1, 2, 3, 4, 5. There's 5 items around it, and the valence number for nitrogen is 5. So if the valence number is 5, that proves that we only have 1 pair of lone pairs on that nitrogen. Okay. So knowing that, we now have the option of also taking these lone pairs and moving them towards this carbocation now. And lone pairs go to double bonds, and double bonds go to lone pairs. Only if you start with those lone pairs, like what we're doing right here. So showing that bond shift, electron pushing of the resonance, we get this now. Okay, and we didn't move this. We did move this. That now is a double bond, and it still has this around it. And so now that we moved that bond, we moved this bond over here, right? So now this just lost another domain around that nitrogen, right? So that's how we know that this nitrogen will now have that plus charge. So showing nitrogen now have that plus charge, oh actually I forgot this, so we didn't do anything with this, right? If you forget that on your test, you're not going to get the points. So it's always important to look at what you have, what didn't move, and always translate it perfectly onto the other structure. So that's it for that, because over here the only thing we can do is literally, we can't even do anything because we have the charge here and there's not an adjacent double bond off of anywhere from this carbocation or this cation on the nitrogen. So we know we're done with that side. So now what we need to do is go from this side. And what we're going to do is continue here, okay, and show that this bond is going here now. So I'm going to continue that down here. Move this up a little bit, okay. So this doesn't change, this doesn't change, and this doesn't change. And again, we finished that, so we have to refer back to the original picture. That's why I copied it exactly that way. Okay. Okay. All right. So we moved this bond up here. So this bond is now up here. This bond is what just got removed, right? So this spot over here is now going to have that carbocation. And so now we want to continue this further, right? And yeah, so we can now move. One second, I want to double check I'm doing this right. Yeah. Okay, so sorry about that. I was just really trying to see if I was doing it right. Okay. So yeah, we're gonna move this bond here now because we want to move it towards the carbocation, right? Didn't move that. Didn't do anything with that. And now this bond is here, and now this carbocation is now on this spot over here. So the major thing with resonance structures is you want to make sure you don't draw any repeat structures. So I was making sure I wasn't going to do that. And as you can see, the spots are all on different spots. And to complete it further, we see that if we move this here, we continue it further on. So now that double bond is going to be there, carbocation is going to be there, this doesn't move. Okay, so just to test yourself and see if you're supposed to go any further, you're going to compare and see. So if you were to move this here now, like, let's kind of show that, but in a small little side note. So yeah, you would see that this plus is going to be on this carbon, and we already showed that actually, if you look. So this structure is already shown up here, right? We had this bond coming here, making the carbocation on this spot right there. But we already showed that. If you draw a repeat structure, she will probably take points off, so you should know when to start, when to finish, right? So the total structures that you're gonna have drawn for this question is 5, because you had one spot here, you had one spot here, 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 and here. So you have 5 structures totally drawn out. But the thing is that you have to know what is the more stable one. And what we did learn in our sessions, and you learned in class, is that carbons never like plus signs ever. That's like super important, okay? Over here our carbon has a plus sign, which we started with, and when we moved it, it came here. Then we have another one with the plus over here. We have another one with the plus on the carbon here, and another one with the plus on the carbon here. The only one that doesn't have that is this structure. So that's how we know that one's a major contributor, because it's the most stable structure. Okay, so this was actually one of the longer resonance questions that we've seen so far. This is our 3rd test we're going through together. So if you need more practice with resonance, just try to do some worksheets or extra practice through Zaid Faraj, or go through the notes that we made together in the 2-3 weeks leading up to your exam. So that's that one. Your total picture is going to have 5 structures. 1, 2, 3, 4, 5. I'm not counting this because this is what we started with. And you just need to work from there and see which one's the more stable, or the more the major contributor. That's the term. So you need to circle it just like the question said. Okay? Next question. Okay. This one is saying to place the compounds in increasing acidity. Okay, so let's draw the structures. Okay, so these are the 3. And our job is to compare all 3 of these, right? So as you can see, these structures are identical from the left side completely. They're absolutely identical on the left side. The thing that makes them different is how they're bonding with the hydrogen. So these are all acidic actually. They have some sort of acidity in them, but the degree of acidity obviously is different. That's why the question's asking us to rank them. So if you were comparing just these 2, right? The trick you would do is just to remember the electronegativity trend, right? We know that electronegativity goes from left to right, and that oxygen is more electronegative. So that would tell us that this is going to be more acidic than this, right? So this should have a higher number, since the question asked us for ranking and increasing acidity. Now, if you look at this, you see that it's a sulfur. We went over this yesterday, actually. We had the example of comparing oxygen and sulfur. Thing with group 6, or any, in group 6, is that the more you go down, they increase in size, right? And since they increase in size, that's the trend that you're going to use, because the first thing is electronegativity, right? And then from there, you look at the atom, and then you look at size. Since both of these are in the same group, that's what you're going to do. You're going to compare these two, and since sulfur is right beneath oxygen on the periodic table, it has that higher size, so that's how you know that this one's going to be more acidic than this. And if that's the case, then this one's obviously going to be last because of the electronegativity rule between these two, and this one's going to be 2. So that's how you do that one. So it's a good thing to just remember that group rule. If it's in the same group, you go down with size. Okay? Next question. Okay. This next one is asking to draw the structural isomers resulting from monobromination. And again, she can give you any halogen. She can say monochlorination, monobromination, monofluorination, or monoiodination. She can say any of those. So it's just your job to know what this long word refers to with the element, right? Okay, so the structure that we're given in this question is right here. Make sure I drew it right. Yeah, I drew it right. Okay. So our job is to add one bromine, one for mono. She can sometimes say di or tri, it just depends on the question. But this question is saying to add one bromine. So our job is to see how many unique spots are there on this structure, right? To see if we put a bromine here, how would it compare if we put a bromine there, or any of these other spots, right? So the first thing you want to do is label the spots. So if I'm gonna label them with letters. So if I label this as A, okay. Don't worry about if your letters compare with the letters that you might see in the answer key or anything. The place you put the letters and what letter you put in that place doesn't matter, but it matters if you mess up with the uniqueness of those carbons, right? So over here, if we put A here, that's a totally different spot than here, right? As well as this, and that. But this spot is identical. So like putting a bromine here would be the same as putting the bromine there. So we know that these two spots are the same. Now, if we were to put a B here, we have to compare how it compares to the rest of them. So we for sure know that it's not these three, because if we put a B here, that's not going to give us the same spot of the bromine. So we know that the B is by itself there. Same with this and this, right? So the next spot would be here, and we see that this spot is completely unique from all the other spots, but these three are the same. So that's how we know that these will have the same, right? Okay, so as you can see, we have A, B, C, D, E, F. So we have 1, 2, 3, 4, 5, 6. Let me make sure I did this right. sorry, I think I did this wrong. We're going to do this one more time. Okay, so we know these two are the same, right? A and A. These two are for sure the same. Yeah, these two are for sure the same. So AA, B, C, 1. Yeah, okay, no, I didn't do it wrong. I did it right. Okay, A, B, C, D, E, F, F, F. So we have 1, 2, 3, 4, A, B, C, D, F. Okay, so right here, let's draw the first one, right? So we have that structure. Okay. So if we were to draw the bromine on A, we'd get that extra bond and we'd show the A right there. We wouldn't put it here because it would be the same. So 2 would be on the B spot. So this would be the other spot for B. 2 corresponds to B, 1 corresponds to A, and the third one would be for C, and C is right here, so that's where the bromine is going to go there. Next, we have 4. Okay, so A, B, C, D. Right here. Okay. And 5. We did it here, 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 here. And now what we need to do is put it 2, 3, 4. So yeah, now we need to put it right. Now the mistake that this person made on the test, actually, that I'm looking at, in the key, they put 5 bonds on the carbon. That's why it was taking me a while to figure out what they did. But so in the 5th structure, you see that before I even draw the bromine on it, this carbon, how many bonds does that carbon have? It has 4 bonds on it already. So can we even add a bromine on it, even though it's a unique carbon, which we drew an E for? No, we can't. We can't draw anything on it because it already has 4. If you were to have drawn this, that's wrong. You can't show 5 bonds on a carbon that has 1, 2, 3, 4, 5. We know that's wrong. You can't put 5 bonds on a carbon, so I'm going to redraw it. Okay? And this is 5. The place that we have left is after E, which is F, and it can go on either one of these 3. So I'll put it right here. Sorry, no, that's the number 4. I'll put it right here. Okay? So we have 5 structures. This is representing E. This is representing D. This is representing C. This 2 is representing B, and A was representing 1 was representing A. So we're going to have 5 structures. The important thing was to realize that spot E already had 4 bonds on it, hence why a bromine doesn't go on it. So we only have drawings for A, B, C, D, and F. So on your test, all you need to show is this figure, this figure, this figure, this figure, and this figure. The key has it wrong, so don't look at the key and be like, oh, it's not matching up. Well, even though they got the points, you have to realize that TAs always grade papers, and sometimes they let points go, sometimes they don't. So, yeah. Okay. Next part of the test. Number 8. It says consider the following structure below and answer the following questions. So let's do that really quickly. Okay, so finished writing the question. So in this, we're going to do 3 parts, A, B, and C. And A is saying to write the hybridization of each atom indicated in the box. So over here. So what's the hybridization of this? We got 2 domains around it. So 1 and 2. So that means it's going to be SP. You can remember it as like S1P1, 1 plus 1 is 2 for 2 domains, so hence SP. Next we have this one right here, but we do notice that there's going to be a resonance on this question. And since it's going to be a resonance, we have to make sure we're moving stuff properly to make sure that we're getting the right hybridization for it, right? So we have 1, second domain with the hydrogen 2, then 3, but we have to move these lone pairs away, right? So yeah, so then that would become 1 domain with the 2 double bonds. 1, 2, 3. sp2, s1p2, 1 plus 2 is 3, 3 domains. That's how you can do that. Okay, next one we have nitrogen. 1, 2, 3. 3 domains, so 1, 2, 3 domains is sp2 again, s1p2, 1 plus 2 is 3. So we took care of A. Okay, now B is saying to tell us what the bond angle is. CC, CD, NE is, right? So whenever you have this, your job is to look at the middle intermediate carbon that's labeled, and what you have to do is give the bond angle of that middle one, that middle intermediate one. So if you look at CD, which is right here, which you haven't looked at yet, you have that carbon bonded to 1 domain on the left, 1, 2 domains being the hydrogen, and then 3 domains being this double bond. So you have S1P2 SP2 for those 3 domains which we just went over, and we went in our review sessions that SP2's bond angle is 120 degrees, so that's what you put in the box for that answer. So B is done, and C now. Well, we're about to do it. Okay, so it says the sigma bond, what does sigma bond mean? Sigma bond means single bond, okay? It says the sigma bond between the atoms labeled A and B form the overlap of what types of orbitals? Okay, so what we're going to do is just pretty much see what those 2 bond orbitals are, those hybridizations are, and we're looking for A and B, so these 2 right over here. So that carbon has 3 hydrogens, so far it has 3 domains, and then it has that 4th domain connecting that carbon to the other one. So 4 domains means sp3, s1p3, 1 plus 3 is 4, and that's overlapping with this one, with this carbon, 1 domain on the left, 3 bonds on the right, so that's 1, 2 domains. So we have SP. So the answer is going to be the sp3 sp orbital overlap. Okay, next question. This one is going to be a Newman projection question. So let's do that. Let's draw the structure first. Okay, and it's saying to draw in the blank test, yeah, it says to draw the most stable, okay? So that means staggered and 180 degrees anti for the big groups, or the bulky groups, okay? And the question is saying to look at the carbon-3, carbon-4 bond, right? So we're going to look at the carbon-3, carbon-4. So now what we need to do is figure out which way to number this structure and look at it from there. So if we number it from here, we get 1, 2, 3, 4. First substitution on 4, but if we do it from here, we have 1, 2, 3. So we have it on 3. So that's how we know we're going to go from this side. And I usually always end on the carbon that is mentioned in the bond that it's looking at, right? So this is the eyeball. Okay, it's looking at the structure this way. Think of you're looking at the structure, right? And I went over how hydrogen is the fourth. I went over how hydrogen would be on a dash, while this one would be on a wedge. You don't have to show this to get points, but it's just a good way to understand the orientation in terms of the Newman projection. So hydrogen is going to be on the dash because it's the lowest priority group. You're going to learn that in the second and third test of this class. So just factor that into your mind, that hydrogen is going to be the fourth least priority group. So if you're looking at this paper three-dimensionally on the side, like if you hold the paper against your face to where you're looking at the edge of it, if you look at the paper, since this is pointing three-dimensionally out of the paper, this would be pointing to your right. So that's why I'm going to draw CH3 on this, okay? And then hydrogen would be going the other side of the paper. So that's there. Now on this spot, what we're going to do is see what that other gigantic group coming off 3 is, right? And that is this CH2CH3 group. So that's what we're going to put on this carbon. So basically, this mediary point in the middle represents carbon 3, okay? And on carbon 3, it's going to show you what is on that carbon 3. Okay? Now, this circle, for Newman projection rules, you have to draw the circle inside. And what? Okay, let's show. That middle point in the middle is carbon 3, right? This gigantic circle represents carbon 4, okay? So we want the most stable conformation, or aka lowest energy. So if we want the most stable one, then we draw them equally distant from each other. And if we want the most stable one, we want the highest group on this spot, because the highest group on the carbon 3 is this, right? So yeah, so over here on 4 we have the similar thing with this on the wedge pointing up, H pointing inside the paper. So we know that since it's going to be staggered, we want that CH3 group on the absolute opposite side of each other, because they're supposed to be anti. The H is going to be on the opposite side, and then this gigantic group has 2 CH2s and a CH3. So you do that on the structure. Okay. So on your test it asked for the most stable, but if you look on the answer key, it's going to show you that it changed it to least stable for some reason. So just to show, drawing this converted to the least stable representation. So we're gonna translate the original 3 points exactly how they are. But if we want the least stable, so this one's the most stable, right? This one we're drawing is the least stable. Okay, so what we're going to do is pretty much understand what goes where, right? So if we're doing the least stable, then the proximity to all the pieces are going to be next to where the original ones are. So we want two of the bulky groups together if they're going to be, sorry, let me show you all what I'm doing. We want both of the bulky groups to be close to each other, so we're going to draw that other one, the CH2, CH2, CH3 next to that like this, and then over here we're going to do CH3, and then over here we're going to do H. So this one will be the least stable one, so that's how that one would look. So on the blank one, it's asking you for the most stable one, so it's going to look like something like this, and the least stable one's going to look something like that. Okay, and she can ask you both ways on the test. Okay, next question. This is cyclohexanes. Okay. So like before I even start the problem, I just, draw the chairs exactly how they're supposed to be drawn, with 2 for each. Okay, so now that I've finished that, we can now number the structures, and it doesn't matter which way you number it because this is not nomenclature, this is for positioning, right? So I'll just do it like this. Okay, so 1 is down on this first one, so I'm going to go to 1, and 1 down is axial for this one, so do that. And 2, we don't have anything. 3, we don't have anything. 4, we have this structure on 4, and 4 is down, so CH3, 3. So there's 3 CH3s and then another carbon, so there's 4 carbons in the structure. So that's probably going to be the biggest, bulkiest group in this one. 5, we got nothing. 6, we got this CH3 going up. Okay. Let's see what we have. So we have 2 axials and then this equatorial. So if we were to flip it on this one, 1 is down. So down is this right over here. It's on this spot. This corresponds right there for 1. 4 is down. So 4 is down. So that big bulky group is on axial in this spot, so that's not what we want. And 6 is up. So the only equatorial we have are these two over here, right? So if we kind of have to guess, we see that this would be the more stable one because of that bigger bulky group on that equatorial position. So that's the first one. Okay, now this one, we're going to do the same thing. So 1 is up, so that's CH2, CH3 for 1, 2 nothing, 3 nothing, 4 down. So we got that equatorial position for that big group. 6 is up. So we have 2 equatorials, and 2 of the biggest groups are on those equatorials. So we know this is probably going to be the stable one, but let's just draw the other one. 1 is up, so that's CH2, CH3, 2 nothing, 3 nothing, 4 down. So this big group is on a axial, so that's kind of already telling us it's going to be wrong. 5 nothing, 6 up. So yeah, the 2 big groups are on axial here, but they're on equatorial here, so we know this is the more stable one out of these 2. So this corresponds to that, this corresponds to that. And now the answer is saying which one of those 2 in the boxes that you drew is more stable. Well, that's kind of easy. We just have to see which one has more equatorial positions, and that's this one and this one. This one just has 1 equatorial position. These are 2 axials. This is 1 equatorial. This has 2 equatorials. So we know that B, or the second box, will be more stable. This one corresponds to A. This one corresponds to B. Okay. So let's keep going. Okay, we're almost done. So let's draw what they gave us. Okay. Yeah, and see, I just saw your message in the group me. Yeah, I'll do that one after I'm done. Okay. So this is what we're given, and it's saying for this question to provide the propagation steps. Okay. So this is what we're going to be doing. Again, I've been told that bond dissociation energy won't be on your test. Hold on, let me fix this. So even if bond dissociation energy isn't on your test, I'm sure this might still be. So let's just go over this, okay? So with initiation, what's going to happen is these bromines are going to create that bromine radical. So when you're in propagation already, you have that radical already created for you. And we know propagation consists of two steps. So we have that original structure from here with its two hydrogens, right? And once with initiation having formed that bromine radical that we'll have right here, you have to show these arrows that are called fish hook arrows coming in each other like this, making this hydrogen leave and in turn enabling you to transfer this radical onto this structure and to transfer this H onto this bromine. So if you carry that forward, you get the radical here with that one hydrogen, and then you create that HBr. Okay, so that's the first part for this. You're just taking a radical, moving it on to the part that doesn't have a radical, and you're moving the hydrogen that doesn't have the radical on it, and moving that hydrogen onto the structure that does have the radical. So the radical and the hydrogen are switching places this way. And then the second part is you have what you have remaining. Okay, you have that radical on this with the hydrogen, and you initially started with the bromine referring to Br2, and again the fishhook arrows coming this way, and you draw like that, and then this one you also coming here. So again, you're gonna move the radical where it needs to, and you move the bromine onto where the radical is. So you continue on, and this is now going to have the bromine, and you have now that extra bromine radical. So this is what you are pretty much doing. Also refer to the notes that I gave that first day I introduced radical halogenation. It's a really good example that I gave. If you could do that, you can do any of them. So now it's saying to consider the termination step for part B, and the termination step means you're terminating the radicals. So what happens is that you have two of those structures, right? That look like this. And what is going to happen is these two are going to come together to form one structure. So once that happens, you're going to get this. And since there's 3 bonds on it, you don't necessarily have to show the H's on it, but I'm just showing you that this is the 4th bond on those carbons. So that termination step is going to look like this. Again, just so you can have good understanding for this, refer to the notes that I gave y'all on bromine radical, on any kind of halogenation. Okay. So to do this last part, again, you just do BDE broken minus BDE formed. This is for the bond dissociation energy questions, but y'all said that it's not going to be on your test, so I guess I just won't do it. But I mean, I'll just write down the answer so you can see it's so easy. There's like, for that 1% chance she might put it on there, even though I know y'all said it won't be, but just in case, you know. This number corresponds to this right up there. Okay, you'll see it. 95 on the chart corresponds to this. 46 corresponds to bromine connected to another bromine, and 68 corresponds to that same structure bonded with the bromine, and then 88 corresponding to that HBr, the hydrogen with the bromine. And when you add those two together, you get a number. Add these two together, you get a number. Subtract them, you're going to get this. And you should know that if you're having a negative delta H, which is what we're calculating here, it's always going to favor the products in your equilibrium. Okay, So yeah. Okay, let me see. So that is the whole test. Let me see what NCO was talking about. Can you send a pic of the work for 10? Yeah, I can just put it here. Okay, you can take a look at it. You can maybe look at it a little longer, just show you how both of them were different. But yeah, I'll just like take a picture of it and put it in the group me too. I see Ozair's comment, isn't SP1 P2 SP3? Yeah, that's right. If I made a mistake in the review, then it was a mistake. If I said something else, then I probably just was trying to go too fast. But yeah, that's right. If I said it wrong, then apologize for that. Would she give us dibromination or dye anything? Yeah, she can. She can get. I think I've seen a question with dichlorination. If I remember correctly, I think 2006 had that, but I'm not sure. Good luck, guys. That was it. I just wanted to go over that one with you guys, and good luck, guys. If you have any questions, just go ahead and ask in the group me. That's what it's for. And as soon as I click finish, this should be up for everyone to view whenever they want. Take care.